Hi girls, this is just an introduction to another lesson, and this one is on simple harmonic motion equations. Now, the reason why we have equations for simple harmonic motion is to make solving problems easy, and the thing is, they're all related to the reference circle and the reference particle, and the connection between the simple harmonic motion particle that goes up and down and the reference particle that goes around in a circle. So I have drawn here a reference circle, and you have two things. So the center of the reference circle is your equilibrium position. So we are looking at equations where timing starts at equilibrium. So at equilibrium, the simple harmonic motion particles here and the reference particles here. Now you can see arrows of different colors. Now these are just representing what's called phasors. So phasors are rotating radius vectors. That means they're fixed in the center and they go around in a circle, and the circle's anti-clockwise. So the red one is what's called the displacement phasor, which is the same as the radius of the circle and which is also the amplitude of simple harmonic motion. So that's a capital A red arrow. Okay, there's a red vector, it's called a phasor. Now, when the reference particle is over here at this position, so that's the displacement. But for anything going in a circle, its instantaneous velocity in a circle is a tangent to the circle. So the velocity vector is actually this way, a tangent to the circle. It's going anti-clockwise. So if you look at the two of these, it's at right angles to the displacement vector. Okay, and acceleration for anything going around in a circle is directed towards the center of the circle. So the vector that represents acceleration, the green arrow, is pointing to the center. So if you look at the three of them, the acceleration phasor and the velocity phasor at right angles to each other, and the velocity phasor and the displacement phasor at right angles to each other. So all the three are mutually at right angles to each other. Okay, now the next one that I've got for you is what happens when the reference particle moves from the equilibrium position and it moves a little bit. So these phasors move along with it. So your displacement phasor is now pointing this way. It was initially like this. So when it is moved, it goes through this angle. Okay. Velocity phasor, it's again a tangent to the circle, but it's different from the previous one. The previous one was like this, and now this one's like that. Okay, so if you can see both of them side by side. Okay, and the acceleration phasor still pointing to the center of the circle. All right, okay. So that's for the reference particle. So what happens for the simple harmonic motion particle? The simple harmonic motion particle is actually, so when it was at equilibrium position, it was here. When the reference particle is there, the simple harmonic motion particle is always in the same horizontal line, so it's there. So I've just put the simple harmonic motion particle. It's on its way up. Okay, when it's on its way up and at this point, displacement is from the center of the reference circle to where it is. So the red arrow pointing upwards, that's your displacement, letter Y. Velocity, because it's moving upwards, that's your velocity vector, okay, pointing upwards because it's moving upwards. If it was coming down, the velocity vector would point down. But this particular instant, let's say it's going up. Acceleration, no matter whether it's going up or down, always points to the center of the circle. So the green arrow represents the acceleration. Okay, so I've shown you these separately. Now let's put them together one at a time. And let's see what's the connection between the displacement phasor for the reference particle and the displacement vector for the simple harmonic motion particle. So in this diagram, they both look identical, and you wonder, why has Mrs. John drawn two of the same thing? There's a reason for when you see the others. So we're starting timing at equilibrium, And after a period of time, so you start time there, and after some time, the simple harmonic motion particles move from here to there, the reference particles move from there to there. So they're always in the same horizontal line. The length of the displacement phasor is the amplitude. Okay, so that's the amplitude, which is the same as the radius. And if you look at it, if we completed this triangle here, this y, which is the displacement of the simple harmonic motion particle, is really the vertical component of that displacement phasor. Okay, I just wanted you to make that connection. This is the vertical component of that. Let's look at the velocity. Okay, so this is the velocity. So when the simple harmonic motion particles here, its velocity is pointing upwards, and the velocity of the reference particle is this way. Okay, so if we look over here, because a phasor is a rotating radius vector, the tail of this has to be at the center. Okay, so the tails of these arrows have to originate from the center, and because the direction is like this, I've kind of just translated that to the center. That's why it's coming like that. Okay, so and the length of this phasor is maximum velocity, which we've seen earlier in the earlier lesson. It's a omega. So that's this. I can't make out, my pen was too thick. All right, and this v is the velocity of the simple harmonic motion particle. Same thing, it's just pointing upwards, but just starting from the origin. Again, this is, if you make this into a triangle, this is actually, again, just the vertical component of your velocity phasor. Okay, similarly, if you look at acceleration, so acceleration for the reference particle is always pointing towards the center, no matter where it is. So I've just drawn the acceleration phasor. And acceleration for the simple harmonic motion particle, even though it's on its way up, acceleration always points down. Now, because the tail of the phasors have to be at the center, if I translate this one will be here, and the tail should be pointing downwards, and that's what I've done here. So again, if you look at this, if we complete this and make it into a right angle triangle, this is again the vertical component of that phasor. So that's what I wanted you to see, that the velocity, acceleration, and displacement for the simple harmonic motion particle is always the vertical component of the reference particle's displacement, velocity, or acceleration. And the length of the phasor for displacement, velocity, and acceleration for your reference particle, your displacement is maximum displacement, which is A, amplitude. Your velocity, the length of this, is your constant velocity for your reference particle, which is A omega. And your acceleration, which is again constant for the reference particle, is A omega squared. Okay, so that's the length of these phasors. However, the acceleration, displacement, and velocity, they all change for the simple harmonic motion particle, like we've seen in an earlier lesson. Sorry, my dog's barking his head off. There must be somebody there. Okay, then bye. Enjoy the rest of your day, and that's the lesson for today. I'll put some notes up for you.